Just go for it.
Well,
It's
I
recording.
mean, I think we should have asked them like if they wanted us to just go straight into study questions, but
Oh, we can ask now and then crop it out later.
So for right now, does anyone have any questions regarding anything specific that they want us to go over first regarding exam 4? If not, we're going to start. No one has anything specific. We're going to go straight onto the 13 study question set. This session will finish at around 6:30. So it's going to be a 2-hour session. But don't worry, you have to leave early. That's okay. This is going to be recorded and uploaded to the Pillar YouTube channel.
I was having some problems with the little geometric patterns and stuff like that. We don't got to go over it now, but like if we could, that would be cool.
We'll definitely go over that.
yep. Anything else that people were feeling a little too concerned or confused about? No?
Yeah, actually, I was a bit confused on the. What was it? I forgot. It was. Or I think it's on the 15th page. I guess when we get to it, I'll point it out.
All right, sounds good. So starting with the 13th set, some of these are pretty straightforward, so let's breeze through the easier ones real quick. So, which of the following pair of electromagnetic radiation has the higher frequency? As you guys may or may not already know by now, higher frequency means that they have higher energy. And for us, the highest energy waves that we deal with on a day-to-day basis is X-rays. So what do you guys think would have a higher frequency, violet or red?
Violet?
Violet, right? Yeah, because it's closer to the UV light. And because it also has a shorter wavelength. Now, for the next one, which of the following pair of electromagnetic radiation has longer wavelength? Radio or X-rays?
Radio.
Radio, right? So nothing too serious, just looking back at what we've done so far. Next one. Which one is the following pair of electromagnetic radiation has the higher energy photons? So which one has higher energy, UV radiation or infrared?
Is it the UV?
UV, right? So since violet light has a higher frequency, we also know that ultraviolet will have a higher frequency, which means it will have a higher energy. Now going into number 4, this is all you need to know about number 4. For the quantum number L, there needs to be a difference of at least 1. So that means that they need to be values that are a whole number, and they can't be the same whole number if it's a different subshell. Does that make sense?
Wait, please can you repeat that? Sorry.
Yeah, so for anytime we're going from one subshell to another, what's important is that it's going by a whole value. So it can't go by half a value or anything like that. If it's going from like the 2p to the 2s, that means it's going down by one whole value. It can't go halfway between the 2p and 2s. It needs to go all the way down to the 2s or all the way up to the 2p and so on and so forth. Does that make sense?
Okay, thanks. Yeah.
Any other questions for 4? No? All right. So number 5, when an electron in a subshell and an excited atom drops into a subshell of lower energy, how many photons of light are emitted? So before we answer this question, can anyone tell me what a photon is? Anyone know what a photon is? A particle of light, right? Okay, so about these particle of lights, what exactly do they tell us? Like, what do they represent? Or what can we get from light?
Energy?
Energy, right? So when it comes to energy, can for a photon of light, can it have any amount of energy in it? It's not a trick question, I swear.
Think of it this way. What takes more effort, going up the stairs or going down the stairs?
Going up the stairs.
So when are
Yeah.
you going to need energy? Going up an energy level or going down an energy level? You see up in the chat? Sorry, Jerry. I'm not even sure if that's the question you were asking.
That wasn't the question I was asking, but that's fine. But okay, but yeah, like these photons can have any set energy. So when an electron's going down, no matter the amount of energy that it's emitting, it's all going to be emitted as one wave of light or one photon. Does that make sense to everybody?
So when it's going like up an energy level, is it also one photon?
When it's going up in energy level, it absorbs a single photon.
Okay, thanks.
Because remember, you need energy to go up an energy level, and a photon is energy. So if you're going up an energy level, you need a photon. If you're going down an energy level, you're getting rid of a photon.
So that's for 4 and 5. So number 6. In the emission spectrum of lithium, one of the lines in the visible region occurs at 671 nanometers. The photons in light at this wavelength result from the transition of the outer electron from the 2p subshell to the 2s subshell. Calculate the energy difference between these two subshells in electron volts from the wavelength of the light, 671 nanometers. So calculating the energy difference is basically calculating the photon. So anytime we see energy difference, we're looking at photon emitted, which means that it should be a negative number, if I'm not mistaken. I'm pretty sure it should be negative, since it's going from a higher energy level to a lower, or if a photon's being emitted. So, but we'll worry about that when we get to the energy portion. So first things first, in order to figure out the energy, well, for energy, we use Planck's constant and frequency. Do we have frequency here yet? No, right? So how would we get frequency? What equation would we use?
V is equal to C over wavelength.
I think I heard you right. Sorry, it's because like you're a little quiet, but I think you were talking about this equation, right?
Yeah, but she can be manipulated.
Oh, well, yeah. So for us, we would have c over wavelength. So c being the speed of light, 3.0 times 10 to the 8th over the wavelength. Since it's in That's not funny. So since it's in meters, we need to make sure that our wavelength is also in meters. So what would be the wavelength in this case? 6.71 times 10 to the what?
-9.
It'd be -9 if we left it at 671, but if we move it over 2, what would it be then? -7, right. -7 meters. So if we were to divide the speed of light by the wavelength, what would we get for our frequency?
What do you mean if you move it over 2? Sorry.
So when we went from nanometers to meters,
Yeah.
what we did was for every for every 1 nanometer, it's 1 times 10 to the -9 meters. And so when we do that, when we multiply that, we'll get 671 times 10 to the -9. However, in order for it to be in scientific notation, we need to move it over so that it's between 1 and 10.
Okay, thank you.
So dividing the speed of light by the wavelength, we get what for our frequency? Perfect, yeah, 4.47 times 10 to the 14th inverse seconds. And the reason why it's 14th and not 15th is because 8 plus 7 gives us 15. However, the coefficient was 0.447, so we need to move it to the right one, which brings it down to 14. So this is our frequency, and we have Planck's constant. So what would we do with this frequency? What would we do with Planck's constant? Multiply it, right? So 4.47 times 10 to the 14th will be multiplied by 6.63 times 10 to the -34. And that gives us 2.96 times 10 to the -19, right? And once again, it's -19 and not -20 because the coefficient was 29.6 and we moved the decimal to the left one to give us 2.96. Now, are we looking for energy in joules, or what's the question asking for? Electron volts, right? So how would we get the energy in electron volts from this number right here? Right, so we'll divide by 1.60 times 10 to -19, and that will give us electron volts. So divided by 1.60, and what do we get? 1.85 electron volts. Is that our answer? Right. So when it says energy, since it says calculate the energy difference between these two subshells, we're calculating that change will be positive since we're looking at it from the photons. Does it make sense to everybody? Any questions on 6? No? All right. So number 7. In Mendeleev's first periodic table, elements with similar properties were lined up in rows rather than columns, which is the case in modern periodic tables. He left 2 spaces blank in the 4th column between zinc and arsenic. Why did he do this? Does anybody have any idea why he did this? All right, so what Mendeleev happened to notice while he started to put elements by their increasing atomic mass was that, like it says here, that there would be a periodic repetition of properties. And so he predicted that there would be elements between zinc and arsenic that would follow those repetition of properties within that same column. And this is how we got germanium. I didn't write it down, but does that make sense to everybody?
Can you repeat it one more time?
Right. So he had left these 2 spaces because he had noticed that there was a periodic repetition of properties. So when looking at the increasing atomic mass for each of these elements, what he noticed is that, well, between zinc and arsenic, there seemed to be like a gap when it came to the repetition of the properties for the same elements in that column. So he predicted that there would be an element in between zinc and arsenic that would follow the periodic repetition of properties there, which was germanium and gallium. Does it make sense?
Yes, thank you.
Does anyone have any questions for 7? No? All right. So 8, as one proceeds from left to right in the second period or row of the periodic table, there is a rather dramatic increase in ionization energy with 2 anomalies, one being between beryllium and boron, with boron's ionization energy being lower than that of beryllium, and the other between nitrogen and oxygen, with oxygen's ionization energy being lower than that of nitrogen. Explain, first of all, why the ionization energy increases from left to right with the exception of the anomalies, and secondly, explain the anomalies. So, can anyone tell me why the ionization energy, the first ionization energy, increases from left to right? Any ideas? Because there are more electrons to the right. Close. Like it's right, but there's something more specific that I'm looking for. Like there are more electrons, but what does more electrons have to do with ionization energy?
Is it to do with the nuclear charge?
Nuclear charge.
So does it increase? So it drags in the electrons more.
Well, yes, but that's when going from bottom to top, like the atomic radius. So for nuclear charge, it can be a little confusing. I think for question set 14, there's a question on it, and so we'll get more into nuclear charge there. But it's something like less specific. So for ionization energy, what exactly is happening for ionization energy? What are we doing to the electrons? We're taking away an electron, right? So if we add more electrons, what's happening to that shell?
It strengthens the shell, so
Right.
it's harder to take one away.
Exactly, right. So as we're strengthening, adding more electrons to this shell, it's becoming more full, it's becoming more stable with more of these electrons. So getting rid of an electron will make it become less stable. That's why when looking at fluorine compared to, say, lithium, fluorine's a lot more stable if it gains an electron than if it loses one, compared to lithium just wanting to get rid of one because it's by itself. Does that make sense? Why it increases from left to right to everybody?
Can you say that again?
Right. So as we add more electrons on with the increase in protons going from left to right, that outer shell is becoming more and more stable. It's becoming more like a noble gas. And so as it becomes more stable, if we were to remove an electron, that would make it less stable, which is not what the elements want to do. That's why lithium, it's easier to take an electron away from it than it is from fluorine, because fluorine's more stable than lithium is with that second shell, sorry. Does that make sense?
Yeah.
All right. Now for these anomalies, let me draw it. So let's look at beryllium and boron first. So beryllium, it only has its 2s subshell field, right? So it looks like this, 2s. So this one is completely full. It's one of its subshells is completely full. Completely full. Now let's look at boron. Now boron has its 2s subshell full, but it also has one electron by itself in the 2p. So it'd be a lot easier to get rid of an electron from an orbital that's not full than to take an electron from a subshell that's completely full. Does that make sense? Yeah, everybody understands why it's easier to take this electron right here away in boron than to take this one right here away in beryllium? All right, I'm seeing yes in the chat, sounds good. Now let's look at nitrogen and oxygen. So nitrogen and oxygen, they both have their 2s's filled. So we can't really use that. But nitrogen, 1, 2, 3, has one electron in each orbital. So it's pretty stable with half of its subshell filled. Oxygen has an electron in each orbital, but it has another one in one of its orbitals in the p. So if we were to take away this electron, the p subshell will still be stable because it will still at least have one electron in each orbital for that subshell. When looking at nitrogen, if we were to take away this electron that's in its subshell, that would make it less stable because now it doesn't have each orbital with an electron. Does that make sense? Any questions about why Oxygen has a lower ionization energy than nitrogen. No, makes sense. Okay. Now for number 9, in each period or row, which element has the highest electron affinity? So basically, I'll give you guys a hint. They're all in the same column. So what column has the highest electron affinity? The halogens, right? And why would they have the highest electron affinity? What's another fact about the halogens when it comes to each row that they're in? Well, they don't quite have full valence shells, but they do want to have full valence shells. So what does that tell us about them? Electric, uh, for example, fluorine in the first or in the second row. What makes fluorine different from the rest, I guess? It's the most reactive. Okay, what's another way of putting that?
Is it more electronegative?
Beautiful, yes. So all of these that have the highest electron affinity also have the highest electron negativity.
Is that just because it just needs one more electron?
Perfect, exactly. So since it just needs one more electron, it's a lot more likely to pull in that electron and accept it. When accepting electrons, they give off energy depending on how badly they want an electron. So like, for example, let's say we're looking at lithium. If it were to pull in an electron, a second electron, it would need a lot of energy to keep that electron from staying with it because it only has 3 protons to help keep that in, whereas fluorine has 9. So it has a stronger pull. It wants that electron more.
So if it was like a band, lithium would be like a triangle player, and fluorine would be like a full band that just needs a triangle player.
Yeah,
All right, I
that's
get
one
it
way
now.
of thinking of it.
You just made it all click.
Well, yeah. So that's how it is for rows 2 through 7. However, there is one row that does not follow this trend. So let's say we're looking at the first row that has hydrogen and helium. Which one would have a higher electron affinity, hydrogen or helium? Okay, I see a helium.
Hydrogen, because he's just missing one person, right?
Beautiful. Yes, exactly. Yes. Hydrogen will have a higher electron affinity because it's missing that one person. It needs one more electron. So the noble gases won't really have a high electron affinity because it's already full. They have full shells. They don't really care to take an electron or to give one up. They're just there, taking up space. So yeah, it would be hydrogen. And boom, just like that, we finished question set 13. Any questions for question set 13? Does it all make sense? Yeah. All right. So going straight into question set 14.
Here, Jeremiah, you want me to cover this for you?
Go for it, my guy.
All right, here. Can you stop sharing your
Oh,
screen
and
because
I
I
was
haven't.
supposed to-
Oh, actually, wait. I want to do number 1 first.
Yeah. Oh, yeah. Explain them the effective nuclear charge. Mhm.
Please,
All right.
thanks.
I had a feeling. All right. It's funny because I legitimately just learned about this yesterday in PChem. So, okay, guys, let's ignore the effective nuclear charge for a second. Let's say we're looking at like the elements on the periodic table. What element will, so which one's bigger? Lithium or potassium?
Potassium.
Potassium, right? Because it has more levels. Now, keeping that in mind, which one will be bigger? Potassium or bromine? They're in the same row. Potassium would be bigger, right? And why do you guys think potassium would be bigger?
Because it has less protons to pull in the electrons.
Okay, that has a big role to play. Have you guys talked about any other things that may be why it's bigger? That starts with an S?
Has like less shielding.
Right. So, fluorine, the shielding doesn't affect them as much as it would affect the ones for potassium because it has more electrons. So, looking at this electron configuration, going from the first subshell or first shell that's closest to the protons and the third one that's furthest away, which one do you think would feel the pull of the protons the least? Keeping in mind shielding.
The 3s.
The 3s, right? So 3s will have the lowest effective nuclear charge because it's the furthest away, so it doesn't feel that pull nearly as much. Now, let's look at the 2s and the 2p. Which one do you guys think would be affected by shielding more? The 2s or the 2p?
Two S.
You say the 2s will be affected by shielding more? Okay, I have one for 2p. Is that what you were saying, Aaron? Because
Yeah, that's what I was saying, but it's probably wrong.
Well, let me explain. So, let's say we're looking at sodium, right? It has 11 protons in the center. 11 protons. So, this is the 1s. And then we have the 2s. So, there's 2 electrons. And then we have the 2p. I'm drawing another one just so that you guys can see the difference for the electrons. It's not another energy level, just so you guys know. So we have 1, 2, 3, 4, 5, 6. So 2p is affected by shielding more because each of these electrons that is trying to pull onto these 11 protons have to deal with the other 5 getting in the way of that one pull. So they're going to have to deal with the effective nuclear charge more. Does that make sense? So these 5 are trying to keep this one away.
They're just bad influences.
What can I say? They're negative.
Ah, look at you, Jeremiah. Get out of here.
This mother.
That was so bad. But
Nah,
also
that
I was
was-
gonna say
that was good.
you could kind of think of it as like competition, right? Because they're all
Yes.
like trying to get the same pull.
They're all trying to get as close to the protons as possible. When you have more competitors in the way, it becomes harder to reach that goal, which is why 2p would have a harder time than 2s. you can think of it as like rank seeds. When there's people in a tournament, some of them are seeded into certain positions. Like they're seeded to be able to participate in the quarterfinals, semifinals, and things like that, because which makes them that much more likely to win the tournament. So you can think of like the 3S as like that boony school that like no one's ever heard of, and you can think of the 1S as like returning champions that are just like coming back to get their chance at taking the win like once again. Does that make sense?
Yep.
All right, cool. Any questions on number 1? No? All right. Go for it, Alan.
All right, can you stop sharing your screen real quick so I can pull up my version of it? Perfect. All right, so let's see, make sure I don't accidentally pull up the answers. There we go. So let's move on to number 2, where it asks us to draw the Lewis dot structures for each of the following molecules. So so let's start off with water. What do I need to do before I start drawing any sort of structure whatsoever? What's the first thing I would have to draw here? So, yeah, that's part of it. Find the valence electrons. So specifically of the atoms that we have for our molecule, since we have 2 hydrogens and an oxygen, let's draw that here. So we have an oxygen with 2 hydrogens bonded to it from the looks of it. And we need to find since it's a Lewis dot structure, we need to do the Lewis dot structure for each atom right now, which does involve their valence electrons. So in order to draw those, I need to know how many each atom has. So how many valence electrons does hydrogen have?
1.
Yeah, it has just 1. Perfect. It's in group 1. So we just put the 1 there. And for oxygen, how many valence electrons does oxygen have?
6.
Perfect. Since it's in group 6, it's going to have 6 valence electrons. So we go 1, 2, 3, 4, 5. I'm just going to put 6 down here. So now we have all of our atoms with the correct number of valence electrons. All it's left to do is to pair any unpaired electrons, either in lone pairs or within bonds. Because remember, electrons love to be paired up with each other. So again, remember, a lone pair is something like this, where we have 2 dots next to each other. So 2 electrons next to each other on an atom. And within a bond, they'll be connected with a line. So you won't really see 2 dots. You'll just see a line connected between the atoms. So which unpaired electrons can I connect to form the Lewis structure for water?
Wait, what? Don't you just draw lines?
Yes, and specifically with unpaired electrons that bond to the central atom, which is here's oxygen. So in this case, we have an unpaired electron on our hydrogens, and we see 2 unpaired electrons on our oxygen. So with those, we can make 1 pair by connecting the 2 like that. And another thing to remember, that you have specific atoms that need to follow the octet rule. And who can tell me what atoms need to follow the octet rule?
Noble gases.
It would be carbon, nitrogen, oxygen, and fluorine.
Yes. So noble gases, they're technically always following it because they're already have a complete set. But whenever we're bonding atoms like this, then yes, so you can think of it as CNOF, carbon, nitrogen, oxygen, and fluorine. So since here I have oxygen, and since the octet rule means that it must have 8 electrons in total, either bonded or lone pairs, does this oxygen follow the octet rule within H2O?
Yes.
Yes.
Yes, perfect. Because here we see we have 2 lone pairs, so that's 2, 4, and then each line counts as 2 electrons, and that's 6, 8. So 2, 4, 6, 8 in total electrons around our oxygen. Perfect.
Well, I'm sorry.
So now
What's
that we
seen off again? What does that mean?
It's the atom, the types of atoms that need to follow the octet rule whenever you're making your structures. So that's carbon, nitrogen, oxygen, and fluorine.
What does that
That's
mean?
just the order that they are on the periodic table. So that means that those are the ones that can't have more than 8 electrons in their valence shell. For sure, 100%.
More or less than 8. So let's move on to HCl, hydrochloric acid. So we know that hydrogen has 1 valence electron, but how many valence electrons does chlorine have?
7.
Perfect, has 7. So we have 2, 4, 6, then 7 valence electrons. Perfect. So obviously the connection here, since we have an unpaired electron on chlorine and unpaired electron on hydrogen, it's clear that we need to make a bond between them in order for them to be paired up. So this right here, this would be our valence structure, or yeah, our valence structure for hydrochloric acid. We're a single bond between hydrogen and chlorine, which has 3 lone pairs. Now that we have that one done, nice and easy, let's move on to CO2. So how would carbon dioxide look like? Since we know that oxygen has 6 lone pairs, how many lone pairs does oxygen have? Oh, did I say oxygen again? Like how many does carbon have?
Carbon has 4 electrons.
Perfect. Since it's in group 4, it's going to have 4 valence electrons. So how can I pair up my unpaired electrons between my atoms here? What do I need to do?
Make a double bond.
Perfect. So let's make a double bond between, let's say, this right oxygen here. So we have these unpaired electrons that can pair up like so. So we have a single bond. But since we have one more unpaired electron here, we can see that we can use another unpaired electron on carbon. So we bring both of them side by side to where they're able to bond like this. Then we can draw the line connecting them. And now we made a double bond. So if that's the case, we see we have 2 unpaired electrons on both oxygen and carbon on the other side. So we can do the exact same thing. We can create another double bond. So let's line them up here and connect the dots. Now, does my carbon and my 2 oxygens, do they follow the octet rule as they currently are?
Yeah.
Perfect, exactly. Because here oxygen, we have 2, 4, 6, and 8 electrons. Since our oxygen's the same on the left and right, we don't have to count our right one. And for carbon, we see it has, starting from the left, 2, 4, 6, 8 electrons total. So both of them perfectly follow, well, all 3 atoms follow the octet rule. So this would be your valence structure for, or your Lewis dot structure for carbon dioxide. So let's move on to CH4, methane. So we have here 1 carbon and 4 hydrogens. Since we know that hydrogen has 1 valence electron and carbon has 4 from the previous examples, what do you think do I need to do here? It's kind of obvious, but what do I have to do here? Let's see here.
It's just me, Alan.
Connect them.
Yeah, perfect. We got to connect the dots. So obviously, since we can't make any lone pairs right now, all we can do is make single bonds with the carbon and each of the hydrogens. So this right here would be your valence structure for methane, or your Lewis structure. With a single carbon with 4 hydrogens on each side, or a hydrogen on each side of it. So let's move on to nitrogen gas, N2. So in order to do this, how do we know, or I guess, how many valence electrons are around nitrogen?
5.
Perfect, 5. So we have 1, 2, 3, 4, and then I'll put my 5th one up over here. Since we know that there are 5 valence electrons around nitrogen, and it's N2, so nitrogen gas, how can I pair up my unpaired electrons in order to have them either paired, either in lone pairs or in bonds?
Make a triple bond.
Perfect. I need to make a triple bond. Because here, if we were to connect one of the pairs, like so, we have a single bond and we have two more unpaired electrons, so we can make another bond. And since we have another pair, or I guess not another pair, but we have unpaired electrons on each atom still, then we can make a triple bond down here. So now that we see that all our unpaired electrons are paired either in bonds or in lone pairs like these electrons, then we know that everything is where they need to be. But before we for sure know, we see that we're using nitrogen. So do both of the nitrogens follow the octet rule?
I guess technically, yeah, if you count all the electrons it gets from its brother.
Exactly, perfect. If we were to count all the electrons, so let's start off with this left nitrogen, where it has 2, 4, 6, 8 electrons total. And since
Does
our
that mean O2 would have a quadruple bond?
no, because the highest type of bond you can go to is a triple bond.
Why can't it have a quadruple bond?
There's not enough space for it, to be more precise, because when we practice your electronic geometry, you'll know, because remember, electrons, they're trying to repel each other because they're all negatively charged. And because of that, you can't have a quadruple bond because the angles will be too close to each other where it's not stable. So right now, this is like, even triple bonds, it's pretty stressful on the atom itself, but it's as stable as they can get to be satisfied, like nitrogen gas here. Does that make sense?
I guess. Do they have pictures of it?
I can actually pull up here, let me pull up a quick little thing here.
So does O2 have a double bond then?
Yes, O2 would have a double bond.
That's
So
weak.
kind of, yeah, you could consider it weak. So the best way you kind of look at it is where single bonds are their strongest because there's not a lot of stress. They're not being repelled by too much. Where double bonds, they're a bit closer together, and triple bonds, they're as close as they can physically get. So let me quickly pull up something, kind of give you guys an example real quick. So let's see, let's go here. So can everyone see like the changing screens right now? We're in the top left, like we have a control panel. Yeah, I see Sophia confirming me. Perfect. All right. So let me show you an example with nitrogen gas. So if nitrogen has a triple bond like so, if I were
Oh,
to
I meant
add,
like a real picture, not a drawing.
oh, this software actually shows atoms in a actual 3D setting to show you what I mean by why quadruple bond can't be possible. So if I was,
Like super magnetic cameras that look at atoms and stuff.
yeah.
I want to see a real picture of it, not being strong enough to do quadruple.
Well, the thing is, it's very hard to take actual pictures of atoms. That's the thing.
There's really no such thing as a picture of an atom
It's
because
just,
remember, electrons aren't stationary, like they're always moving. So the diagrams that we draw are like pictures and what we think they'll look like, but we can't really like capture that. Like, like we compose and take a picture, but electrons don't really do that.
so whenever you see like a videos or like pictures of like those atoms interacting, it's not the actual atom itself. It's more of just the I guess you can say the reflection of electrons, where to kind of put it lightly, whenever scientists shine a beam of electrons to get the image of an atom, they're seeing what the most reflected, I guess the reflected areas are, where like, okay, this is being repelled, so this is most likely the air of the atom. I don't know the specifics of it.
Alan,
Yes.
I have something to say about that.
Yeah, go ahead, say that thing.
So the way that they do quote unquote positions for electrons normally is they do it with a detector. So the way that they figure out how electrons are has a lot to do with uh just detecting where it is. So they force it in a certain area to go a certain way for a certain amount of time until it hits a certain interval, and that tells them, yes, this has this amount of electrons, and these electrons are doing this. Of course, like they have to do it like a lot of times to figure out the certain like habits electrons have, but that's how they do it with detectors.
Mhm. So going back as to why like a quadruple bond is not necessarily really possible is due to all the stress. Because remember, all these bonds, they have electrons in them, so they're repelling each other. But since we have the way nitrogen gas can be satisfied following the octet rule, it has to form a triple bond. But it can't really form a quadruple bond because there'll be too much stress. Because remember how when we go into your molecular structures, that there's certain bond angles, and you'll see that for some of these, you can see that the angle is very tight around these electrons. And if we were to do any closer, the bonds would basically be overlapping with each other, to put to put it in the simplest way possible. And you don't want that because it's like pushing two magnets up against each other on the same end, like two negative ends together. They're going to force each other away. So the more negative ends you add to push up against each other, the more they're going to repel from each other. Does that make sense?
Yep. Thank you.
You're welcome. So let's move on to the other example, which is pretty easy here. Hydrogen gas H2. So we have, obviously we know that hydrogen has one valence electron, and since there's two of them, the only obvious choice is to connect the two electrons. So here's how our hydrogen gas would look. And so let's work on the last molecule we're given, HCN, which is also known as hydrogen cyanide. So we see we have a hydrogen, which we know has one valence electron, a carbon with 4 valence electrons, and a nitrogen with 5 valence electrons. So how can I evenly bond all these electrons up? Who has an idea of what I can do?
Single bond with hydrogen, carbon. And then it looks like you can do a triple bond with carbon and nitrogen.
Mm-hmm. Yeah, we can. So we see all of our unpaired electrons, we can evenly pair them up to the atom next door. So with the carbon with the nitrogen. And remember, the highest you can go is a triple bond. Mm-hmm. Let's see.
So then lone pairs, they just float around then?
Yeah, the lone pair will stay around the atom that it's on. Mhm. So if there aren't any more, because remember, if you already have as many atoms bonded as you can, as many electrons paired up in bonds as you can, remember that electrons like to move around. So if they can become a lone pair on an atom that can accept a lone pair, so either an atom that has missing electrons for the octet, or say an atom that's not involved in the octet rule, where they have space in their shell to accept it, then they'll take the lone pair, for example. If there's like two unpaired electrons around, but you can't make a bond between those two atoms. We'll go over that when we'll cover that when we go over your oxo anions down here. But right now, this is the correct structure for your hydrogen cyanide, where oxygen, we see that it completes the octet rule, where it has 2, 4, 6, 8 electrons. And so does nitrogen. It has 8 electrons in total. Are there any questions regarding number 2? Any concerns? Anyone lost at any point?
Did you answer the question in the chat? Sorry.
Oh, I believe that was like part of it as well. So there are any electrons.
The one about the bonded, the lone pairs?
Yeah, I believe it did because it was both asked and put in the chat. Yeah, so any leftover electrons that you have that are unpaired, and typically if you can't bond, if they're not able to be bonded to the central atom, then they would become a lone pair on the atom that can accept extra electrons. So those that either missing electrons for their octet, or atoms that are not part of the octet rule.
Will there ever be just one atom or one electron left over?
There shouldn't be. For Gen Chem 1, there won't be. There shouldn't be. So whenever you're doing these structures, especially with your oxo anions, because remember the negative
They'll
charge.
either be bonded or lone pair?
Exactly.
All right.
Yeah. So for example, let's move on to number 3 as to show an example, because over here, since oxo anions, whatever charge they have tells you how many extra or less electrons they have. So if it's positive, it means they have, that many less electrons in the molecule. But since, say, for example, phosphate here, for example, has a -3 charge, there's 3 extra electrons. So whenever you're doing something like this, remember to add your 3 extra electrons. So whenever you think you've completed your structure, but you have 1 unpaired electron somewhere, then you may have miscounted your electrons. So you may want to go back and double check how many you have. So let's make some space over here. Oh, didn't mean to do that. So let's start off with phosphate. We see we have phosphorus, and then we have 4 oxygens bonded to it. So we know that carbon has 6 valence electrons. But how many valence electrons does phosphorus have?
5. So does
Perfect.
that mean you double bonds with one of them?
Can you repeat that again? Sorry.
Yeah, it's 5. So does that mean it double bonds with one of them?
Mm-hmm. Well, we'll see what it can double bond, and we'll see that right now. So now we have all the correct number of electrons for all of our atoms right now. But remember that it has a -3 charge, so we put 3 electrons into our structure. So for the sake of this example, let's add 1 electron to each oxygen. So I'm going to make the extra electrons red. That way we remember that we added those. And keep in mind that electrons like to move around whenever they're needed. So don't just think that they have to stay in that position. So what's a bond that you guys think I can do right now in order to complete phosphate?
Can we start with single bonds all around?
We can. So let's start with single bonds all around first. So we have this unpaired electron here. I can bond to our phosphorus unpaired electron. And let's do that all the way around with each unpaired electron. So when we do that, we see that we have an unpaired electron on phosphorus, and we have another unpaired electron on the bottom oxygen here. So what do you think we can do there?
Make them touch.
Yes, we can do that. That's another way of saying make a bond. Yeah, let's do that. So let's line them up to where they're in line with each other and make a double bond here. So just to make sure that, not all of our unpaired electrons are paired either in bonds or lone pairs, since we have oxygen involved, do all of my oxygens follow the octet rule?
Yes.
Yes, perfect. All right. Because we see that the single bonded one has 3 lone pairs, that's 2, 4, 6, and a bond that's 8 electrons. And for double bonded oxygen, it has 2, 4, and then 6, 8 electrons in total. Perfect. So just to make sure that we did make phosphate -3- is, remember your formal charge. So how could I find the formal charge of an atom specifically? Let's see. So I'm not looking for the super complicated long equation, just something very simple where you only require 2 numbers. Exactly. So the number of electrons around, or you can say, yeah, the number of valence electrons the atom is supposed to have minus the number of valence electrons the atom actually has within the structure. So what I mean by that, for those of you that may be confused, is what we would do is, so we focus on the atom, we want to find the formal charge. So we want to know the charge of that atom within the structure. So we would draw a box around that atom, and any bond that this line intersects around our box, whatever's inside it will count as 1 electron. So we'll no longer count it as a pair when counting the number of electrons within here. So if oxygen is normally supposed to have 6 valence electrons, as it's supposed to, we subtract it from the amount that are actually inside our box. So if we were to count them, this bond was cut in half, so that's 1 electron. And then we have here, that's 3 in total, 5, 7 electrons total. Remember, we count up the lone pairs as well. So this is going to be 2, 4, 6, 7 electrons. So since there are actually 7 electrons around this oxygen when there are supposed to be 6, then that gives us a formal charge of -1, meaning an oxygen that's singly bonded with 3 lone pairs will have a formal charge of -1. So that would mean that since this oxygen is -1 and it's identical to our top and left oxygen, these will also be -1. But just to make sure that, we need to figure out the overall charge. Because remember, this -3 applies to the whole molecule, not just, the added 3 oxygens. So if I were to find the formal charge for this oxygen here, we see that, oxygen is supposed to have 6 valence electrons, but here we have 1, 2, 3, 4, 5, 6. So that will give us a formal charge of 0. So this bottom oxygen is going to be neutral. So that's perfect. And if we focus around phosphorus, because again, this matters as well. Phosphorus is supposed to have 5 valence electrons, but since we cut all bonds around it in half, it has 1, 2, 3, 4, 5 electrons inside the box. So our phosphorus in the center is also going to be neutral. So what we would do, not 5, it's going to be 0. So in order to figure out our overall charge matches the one of our formula, we add up all our formal charges together. And if we were to add all of them up, we get a total of -3 of our overall charge. So this would be the correct structure for phosphate that is supposed to be done correctly, where we have 3 negative oxygens, 1 neutral oxygen, and a neutral phosphorus. Is anyone confused? Anyone lost by what I mean by this? Any questions so far? Itzel, you have a question?
Yeah, I'm not confused, but my peer leader, when in the workshop, she would tell us to use like brackets and then put the little. Is that like gonna be important in the test, or is he not gonna put that?
The brackets are just there to formally show it. Like that's not a wrong way of doing it. Like so typically if you were to write it down on a written exam, you would do it like this. But I believe on the exam, it'll give you the images, I believe, to like select from.
Yeah, and then the difference between both is like the way that Alan has it right now with the brackets, that's like the lazy way of doing it, basically. And then if you go in and put in all of the charges for each of the atoms, that's like the long way, but they both represent the same thing. They're both correct. It's just whatever way you feel like doing it, basically.
Oh, okay. So, well, in the exam, is he gonna put brackets, or is he just gonna put the charges?
He might not even put brackets. He might just give you the structure, but
Okay,
Yeah.
it depends.
that's good. Thank you.
Yeah, so if you haven't looked at the answers that he emailed you after this study question set, he just has the structure by itself. So you're gonna have to just look at the structure and then work out whether the charges match to the overall charge on your oxo anion.
Yeah, and then he might also ask you like he'll give you the picture and then he'll say which ones have a formal charge and what is the formal charge, because you should be able to figure it out based on the picture. They don't have when you use the brackets, it's kind of like signaling to other people that they should know where in the structure the formal charge goes.
Mm-hmm. So let's work on a couple more examples here because sulfate follows the same logic as well as our carbonate. But let's work on nitrate because that one I feel can get a. Oh, go ahead.
Other than the xenon ones, carbon, nitrogen, oxygen, and fluorine, the other ones can have as many electrons as they want.
Mm-hmm.
Like, because obviously in that one, phosphorus had 10, like around it, you know?
Yes. Yeah, so anything that's not part of the octet rule doesn't have to have exactly 8 electrons. It can have more or less. As long as your other atoms and your electrons, they're satisfied, whether they're bonded or in lone pairs. Mm-hmm.
Okay, so only them 4 follow the octet rule.
Yes.
Okay,
Yeah.
thank you.
Mm-hmm. You're welcome. But keep in mind, if you're having hydrogen, don't make a double bond with hydrogen because it only has 1 electron. It'll only have 1 electron, so don't go making double bonds with hydrogen. Mm-hmm. So let's work on nitrate here, since I know that this one could be tricky for some people. So we know we have a nitrogen with 3 oxygens, and given from the previous examples, we know how many valence electrons they have, where oxygen has 6 and nitrogen has 5. So what's the first thing you would, oh, before that, we see that it's a minus sign, so -1, meaning there's 1 extra electron. So let's just add that extra electron down here at the bottom in red. That way we know there's that extra electron. So how can I bond up my oxygens to nitrogen to satisfy all unpaired electrons?
Is it 2 double bonds and 1 single bond?
So let's do that. Let's make a single bond with this one down here because we only have 1 unpaired electron. Let's make another single bond. Actually, let's make this one a double bond, now that you mention it. So we'll bring our unpaired electron here and we'll move this one over. Oh, my bad, didn't mean to make it red. So you said 2 single bonds and a double bond. So if I were to do this, bring an electron down here to make a single bond, what can I do here now? Since I done this, but I have an unpaired electron nitrogen and an unpaired electron oxygen.
You can double bond that one too.
So let's see what happens if we double bond that right now. So if we were to make this as a double bond, does we see that our oxygens, they follow the octet rule, but does my nitrogen follow the octet rule?
No.
It doesn't, right? So notice how if I were to ignore this electron for now, like say imagine this this unpaired electron in nitrogen wasn't there, we would see that nitrogen would follow the octet rule with the bonds it currently has. So do remember that electrons can move around wherever they are needed to. So and we have an unpaired electron on this oxygen, which currently is 1 away from solving the octet rule. So where do you guys think I need to move these electrons?
To the oxygen on the left.
Exactly. So if we were to move this oxygen to the left and we were to pair it up with the other unpaired electron as a lone pair, we can see now that our oxygen on the left follows the octet rule now. And now that our nitrogen in the middle now follows our octet rule finally, where it has 2, 4, 6, 8 electrons in total, along with the other oxygens. So now to make sure that our structure here has a -1 overall charge, let's find the formal charge. So let's focus on the oxygen to the left. What would be the formal charge for this oxygen? Let's see here in the chat. Exactly, -1, because remember that oxygen is supposed to have 6 valence electrons. And since we cut this bond in half, we'll count it as 1 electron. And if we were to count all the lone pairs up with this 1 half bond, it would be 7 electrons in total, giving us a formal charge of -1 on that oxygen. So since the oxygen on the left is identical to the oxygen at the bottom, having a single bond with 3 lone pairs surrounding them, they're both going to be -1. But what about my oxygen on the right? What will be its formal charge here? Zero, perfect. So this we know here is going to be a neutral oxygen. Now, what about nitrogen? What would its formal charge be? +1, perfect. So since nitrogen is supposed to have 5 valence electrons, but since all the bonds are cut in half, we have 1, 2, 3, 4 electrons surrounding it in the actual structure. It gives us a +1 formal charge. So this nitrogen is going to have a +1 charge. So in order to ensure that we know our overall charge, we add them all together. So we have -1 plus -1 plus +1 plus 0. And in the end, you can kind of notice that this -1 and this +1, no matter which one you look at, they'll cancel each other out and we'll be left with a single -1. So our overall charge for nitrate is -1. And seeing this, our positive nitrogen cancels out one of the negative oxygens. And we're still left with one negative. So we get -1 as our overall charge. So this for sure confirms that this is the correct structure for nitrate. Are there any questions? Is anyone confused on this? Anyone feel a bit lost? Let's see, I'll take that silence as a no. So let's do one last example here where it's not a polyatomic anion out of these two. Let's do here. Remember, this is not sulfite. This is going to be sulfur trioxide. So we have one sulfur with 3 oxygens surrounding it. So we know that oxygen is going to have 6 valence electrons. But how many valence electrons does sulfur have? Let's see here. Perfect, 6, just like oxygen, since it's the same group. So we know that there are 6 valence electrons surrounding it. So what kind of bonds can I make between my oxygen and my sulfur that you can see right off the bat? Let's see, double bonds? So before we kind of go into double bonds, let's start with single bonds. That way we know what we can work with from there. So we can make a single bond with each oxygen for now, pairing at least some of the unpaired electrons right now. And what we see here, we notice that we have 3 unpaired electrons on sulfur, but we have 1 unpaired electron on each of the oxygens. So just like you said, now we can work onto double bonds now, where we pair each of the unpaired electrons together. So if I were to move them around to where they fit, we can see now, oh, let me move to make it look better actually. We can see now that all of our unpaired electrons are satisfied. Now, do all my atoms that need to follow the octet rule, do they follow that octet rule?
Yeah.
Perfect, exactly. Since oxygen is the only one that needs to follow it, it follows it, and they each have 8 electrons in total. So this would be your structure for sulfur trioxide. Are there any questions, any concerns? I'll take that silence as a no. So let's move on to here. So, oh, my bad. So really quick here, let's go. I'm going to go over just one example here since we worked with these polyatomic anions. Since we see that there's, sorry, let me re-explain myself. Since we see that these acids that we have polyatomic anions or your oxo anions with just an added hydrogen, they're going to follow the same structure. So let's first focus on nitrate since that was the most recent one. So we know that we have nitrate that's double bonded to an oxygen with 2 lone pairs on it, and then single bonded to 2 oxygens with 3 lone pairs on each of them. And so we see that we have a nitrogen bonded to it. But remember, this is for -1 nitrate. But since here the nitrate's already balanced out, then that means there's 1 less electron. Or I guess there's not a -1 there anymore. So that's ignoring the hydrogen, right? Because it's within the molecule. So let's get rid of this 1 electron to the left here. And we see since there's this hydrogen bonded to it, we know that the Lewis dot structure for hydrogen has 1 electron. So seeing as we have an unpaired electron now that this nitrate isn't technically, well, it's still -1, but it's bonded to a hydrogen. meaning that that extra electron isn't just coming out of nowhere like we did in the previous example, number 3, but now it's instead coming from this hydrogen. So they'll form a single bond like this. So this here would be your nitric acid with a hydrogen bonded to one of the oxygens, or one of your -1 oxygens to be specific. Does that make sense? Anyone kind of confused or lost by what I mean? So let's do this again. So up here in the chat. So if there are any questions, let's quickly do here our phosphoric acid here, since we worked with phosphate already. So since we know that phosphate has 3 single bonds to oxygens with 3 lone with, well, I wouldn't say 3 lone pairs, but with 3 lone pairs. So PO3 minus 3. And it double bonded to 1 oxygen. Where do you guys think my hydrogens are going to go, since there's 3 hydrogens? Where do you think those 3 hydrogens are going to bond to my phosphate? Let's see. Yeah, on those 3 other oxygens, specifically those 3 -1s. Because remember that if hydrogen is +1, and if these hydrogens on your single bonded oxygens are -1s, then they're going to be attracted to each other. Your +1 wants to cancel out with your -1s. So let me fix this. Let me just get rid of 1 electron from each of them, because that electron comes from your hydrogen. So since we have 3 hydrogens bonded to these 3 oxygens, then our -1s from each of those oxygens gets canceled out by our positive hydrogens here. So with this, we're still completing the octet rule. We didn't change the number of electrons. So here would be your structure for phosphoric acid. Are there any questions? Anyone still lost or confused by what I mean by this, or what I've shown? Let's see, I'll take that silence as a no, and that you guys perfectly understand and don't have any questions. If you have any questions, feel free to interrupt me. So right here, let's focus on this last part right here, where we draw the Lewis dot structures for 3 resonance structures of carbonate, CO3 minus 2. So really quick, or not really quick, but who can tell me how can I draw my carbonate structure, first of all, before I start doing any resonance structures?
Is it a C surrounded by 3 O's?
So you have a carbon surrounded by 3 oxygens. And since we know their valence dot structures, I'll do that real quick. So how can I pair? So let me put the 4 on oxygen. And so also remember, since carbonates are it's a -2 carbonate, then we're going to have extra electrons. We're going to have 2 extra electrons. So I'll just add 1 to the bottom in red and to the left in red. That way we know those are the extra ones. So how can I pair up my unpaired electrons for this structure? Let's see. Perfect. 2 single bonds and 1 double bond. Since we can only make a single bond with the bottom and left oxygen because they only have 1 unpaired electron, let's do it like that. And then we have two unpaired electrons on the carbon and on our oxygen to the right. Let's line them up to where we can make a double bond, like so. And right now, do all my atoms that need to follow the octet rule, do they follow the octet rule? Do my atoms follow the octet rule, guys? Let's see. Perfect. Yes, now they do. So our carbon has 2, 4, 6, 8 electrons, and so do our oxygens. So now it's time to find the formal charge. So given from the practice that we did, noticing that a double bonded oxygen with 2 lone pairs is neutral, has a formal charge of 0 because it's supposed to have 6 valence electrons, and it currently has 6 in its orbit right now. And given from the previous examples, we know that single bonded oxygens with 3 lone pairs are going to be -1, because remember, oxygen is supposed to have 6 valence electrons minus the 7 that are within it around its immediate orbit, equaling to -1. So both of these oxygens will be -1. And over here, this carbon, since we draw a box around it, since carbon is supposed to have 4 valence electrons and it has 4 within it, this carbon is going to be a formal charge of 0. So knowing that our total charge by adding all our formal charges is going to be -2, we now know that this is the correct structure for carbonate. So all is left to do for this structure is to draw our 3 resonance structures, or to be more specific, 2 other structures, because this is one of those resonance structures. So when I talk about resonance, what am I talking about? Who can tell me what I mean when I say the resonance structure of, say, carbonate here? Let's see. Exactly the same structure, but orientated differently. So how can I draw this structure differently, but keep it the same? Like keep it the same structure, but orientated differently. What do you mean by that? Like how can I set it up?
About flipping the double bond, like putting it on the left instead of the right.
Exactly, perfect. That's what we mean by resonance. So you can look at it as changing
Does
the
that
double bond
matter?
around. It does not. It does not, because remember that these molecules are in a 3D space. So say we were looking at this from behind and your friend was looking at the front. You're both looking at the same molecule. You're just looking at it orientated differently. It's not you're both are not looking at 2 different molecules. They're the same one. So if we move the double bond to the left instead of the right, we still end up with the same structure. I'm going to do this, adding these dashes as a little shortcut for lone pairs to save us time. But this is another one. So seeing as we flipped it from the right to the left, what's another place the double bond can go?
And then you added the extra electrons in the wrong oxygen.
Oh, did I? Oh, I see. Yep, I did. Let's see in the chat. And at the bottom, yeah, there's another, we can put that double bond at the bottom as well. So let me kind of fix this up. So let me scroll down here. So carbon singly bonded to 2 oxygens. And the last place we could put a double bond is at the bottom. So these 3 structures for carbonate are the resonance structures for carbonate. We just move the double bond around, changing locations. So are there any questions regarding this practice sheet? Any concerns? Anyone still confused, or any doubts that they have right now before we move on? Let's see. I'll take that silence as a no.
I just have a quick comment about the resonance structures. You can also think about it. The double bond is moving around because remember the electrons aren't actually still. They're always moving around. So realistically, in real life, we know that the carbon and the oxygens are sharing 8 electrons between them, but we don't really know like which oxygen has the double bond, and that's why we draw the resonance structures.
Yeah, so in real time, they're always going to be moving around. So realistically, all of these could be happening at the same time. So if there are any questions, Sophia, would you like to do the next one?
Absolutely not. Just kidding. Yeah, let me share my screen. Study question 15, right?
Yep.
Okay, cool. I'm also going to, well, actually, before I do, I'm going to show 2 slides from what Dr. Alexander sent you guys. If you want to screenshot it or just kind of keep it in the back of your mind, this is what I'm going to be looking at while we do some of these problems. So the first one is this electronegativity, specifically slide number 5 and 6 if you really want to look at it. And 6 if you really want to look at it like that. But that's the electronegativities for when deciding polar bonds. And then the other slides are 9.5. And that one's going to be slide number 2. It's this table right here. That's just what we're going to be using for another one of the problems in this study question set. So in case you're wondering where the heck I'm getting numbers from, this is where they're coming from. Okay?
Are we going to be provided that in the test?
Yes. I don't know if he'll give you like the whole table, but if he puts the questions on the exam, he will give you the information that you need to answer that question. So you don't have to memorize these. So like, for example, if he decides to put, you know, a thermochemical bond question, and he's just working with carbon, oxygen, and hydrogen, those are the energies he'll give you, and you won't need this whole table, but you will get whatever you need. And then for the electronegativity one, I think he does give you the whole thing. I'm not 100% sure, but you can also use the trends that we've been, that you should have learned, or you should have talked about in workshop, which is like the one where the electronegativity increases up and to the right towards fluorine, or yeah, to the right.
And that's used for determining if it's polar or not, right?
Yes.
Okay.
Cool. Alrighty. So then now I'm going to share the study question sets. Let's see. I'm feeling purple today. Okay, so I think somebody asked at the beginning about the geometries. So yay, we got to them. So one thing to do for these, a good idea when you're figuring these out, is drawing the Lewis structure and then saying the geometry. So remember, Dr. Alexander only wants you guys to learn up to tetrahedral, I believe. So that's the magic number 4. That's the back cover of your workbook. Yes, I ripped mine out. I have a couple workbooks. Okay, anyway, so I don't think you guys will want to do all of them because we only have half an hour left. So anybody want to take, anybody want to request any of these molecules that they're not sure about? Geometry-wise?
Let's do CO3 too.
CO3 too? Oh no. Okay, so we're gonna do this one, and then let's see, what does the chat say?
They said like they want to go over ones
Okay,
with their
one with
ions.
an ion. Okay, cool. So CO3 2 minus, what should I draw for my Lewis structure?
The C with 3 O's around it.
C with 3 O's around it, okay. And then I should have 1, 2, 3, 4, and then 6 electrons in each of the oxygens, right? 4. Oh, I feel like I drew that wrong. Okay,
The
I'm
2
gonna
of
draw it
them
like
get
this.
7.
3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, and then we have 2 extra electrons, right? Whoa, I drew way too many electrons on that one. Okay, I'm gonna, oh no, I didn't. Okay, then we have 2 extra electrons. I'm gonna add one here, and I'm gonna add one here because I can. So where can I make double bonds and where can I make single bonds?
Do a double bond with the one that doesn't have the extras.
Okay, so double bond here. Gonna erase the extra electrons.
And then the other two get singles. So then you get 3
Single
lone
bond.
pairs on all of them.
Alrighty, and then we know from past experience, right, that this oxygen with 3 lone pairs is going to have a -1 charge, right? And then this one's exactly the same, so this is also going to have a -1 charge. Yes.
Yep.
So then we have an overall charge of 2-, which is what we want, right? Okay, so then now for the geometry, we're going to look at the central atom. Remember, it doesn't always have to be the one in the middle, but for now, we're going to stick with the one in the middle, right? That's going to be carbon. What do I need to figure out now to decide on a geometry?
Look at the bonded regions and the lone pairs around the central
Yeah.
atom.
Yeah, look for the bonded regions and the electron pairs in the central atom. So I'm going to call BD bonded regions. How many bonded regions do we have?
3.
3, right? Because this double bond, even though it's a double bond, right, it's connected to the same oxygen, so we count it as 1 bonding region. Yes? Oh, this should be BR, bonding region. Okay. And then how many lone pairs do we have?
0.
0, right? So what is our magic number?
3.
3, right? Okay, so can somebody tell me, according to the magic number and the number of lone pairs and the number of bonding regions, what our electronic geometry will be and what our molecular geometry will be? Oh, I should leave more space for that. So we said our magic number is 3, right? So what are our options for electronic geometry for magic number 3? Starts with a T. Trigonoplanar, right? That's our only option, right? So we don't have to trigonoplanar. Please fix my spelling if I spell something wrong. Okay, yes, trigonoplanar. Is that our only option? For a magic number of 3? For electronic geometry?
Yes.
Yeah, right? What about for molecular geometry?
We have trigonoplanar and bent.
And bent, right? How do we decide between trigonoplanar and bent?
We look at our bonded regions and our pairs.
And our lone pairs, more specifically our lone pairs, right? Because if we have lone pairs, then our molecular geometry is going to be different from our electronic geometry, right? So how many lone pairs did we say we had? 0, right? So then what should our molecular geometry change from our electronic geometry? It should be the same, right? So then our molecular geometry should also be trigonoplanar. Does that make sense to everyone? Yes? Okay, cool. Do you guys want to do another one or you're good? Gonna take that
You
awkward
should do
silence
sulfur
as you're good.
dioxide.
Sulfur dioxide? Okay,
Yeah.
let's do it then. I'm gonna erase, oh, that's not what I wanted to do. I'm gonna erase this and the dots to the best of my abilities. And then I'm going to erase this. Okay, sulfur dioxide. While I'm erasing, can somebody tell me how should I draw sulfur dioxide? Or which one is sulfur dioxide in this list of lovely compounds that we're given? Anybody? Anybody still there? SO2, yes. Okay, so then how should I draw my structure for SO2?
An S with a O on both sides of it.
Okay, we have an S with oxygens on both sides of it. Okay, and then how should I set up my bonds? How many bonds should I have? Or how many electrons should I have around each of these?
They both have triple bonds.
They both have triple bonds. Like this?
Yeah, let's do that.
Does anybody disagree with Aaron?
Or maybe it's double bonds
Maybe it's double bonds. Anybody want to help Aaron out?
with a lone pair in the middle, two lone pairs
The
on
lone
the
pair in the
sides.
middle. Okay, so Aaron's
Maybe
changing
it's
his
single
answer
bond.
to. I think Aaron is guessing. Anybody want to help Aaron?
I like triple bonds. That just gets it one and done. That's all
One and
of them
done.
mixed up.
Anybody want to help him out?
That one looks right too.
That one looks right. I guess this is just.
Just remember
Aaron,
formal charge
hold
for
on.
each element.
Yeah, let's figure out formal charge for this. How about that? You and me, Aaron. Alrighty. If we cut up this box, or the sulfur, right? What is the valence of sulfur?
6,
6. And how many electrons do we have here?
6,
So what is this formal charge?
0.
0, right? And then what about these oxygen?
Same thing.
Same thing, right? So is this good formal charge-wise?
That'll pass. I'll allow it.
You'll allow it. Okay, that seems fair. You are gonna use double bonds. Oh, thanks, Destiny.
Series anyways.
I just barely saw that. Okay, cool. Alrighty, so now let's do the geometry for the sulfur bond in the middle.
How do you find the magic numbers? That just how many are bonded to the middle one?
Yeah, it's basically how many different things you have bonded. So for example, so it's gonna be like
So it's
this
2?
region, and then you're also gonna count lone pairs. So your
So it's
magic number
3?
here should be 3. Exactly. All you have to remember is because some people sometimes they count like a double bond as 2, but it should be just one bonding region. So you have bonding regions. We just said we had 3, right? And then how many lone pairs do we have?
Looks like 5 lone pairs.
Just on the sulfur,
Oh,
1, right?
so we just counted on the sulfur?
Yeah, so when you're counting the lone pairs for geometry, you're focusing only on the central atom. In this case, we're focusing on sulfur.
Okay.
Okay. And then what is our option for naming the electronic geometry based on 3 bonding regions?
I'm guessing it's trigonal also.
Trigonoplanar, right? And then we
What'd you call
have
it?
how many? What was that?
Nothing.
So for our molecular geometry, now we have to consider our lone pairs. So how many lone pairs do we have?
1.
1, right? So is that going to change our geometry, or is it going to stay as trigonoplanar?
I don't know. I don't think it'll change anything. If you have
You
a
don't think
feeling
it'll
it might.
change? Destiny says it changes. Anybody
It'll
want to break
keep
the
it.
tie? What does the table at the back of your workbook say if you have a lone pair?
Do I get to use this table on my test?
No, sir. You have to memorize it. But
3,
there's good
1.
news. You only have to memorize up to tetrahedral. Destiny says it's bent.
Yeah, that's
I
what it
agree.
says. I only got to memorize to what?
Tetrahedral. So magic number 4.
Okay.
So that's the good news.
Oh, and I kind of want to add this. Dr. Alexander, like, instead of using bent, he'll use the word angular. It's the same thing, but in case you get confused and you see that instead of bent, then just know that they're the same thing.
Same difference, different word. Kind of like how he uses molecular instead of covalent bonds. Same difference. But yeah, do you guys want to go over another one, or should we scroll down to see what we can cover? What was that?
So he does it the way it's done in the 50s. Let's go over, I don't know. What's the next step? What's going to help me on this
Do
test?
polar bonds.
Send me some stuff
Or
that's
we
going to
could-
help me on this test.
I guess, okay. He said he was
Yeah,
gonna
what
put
if-
for sure this last question on here. So you guys want to go over that?
We know hot dogs and wieners.
Can we go over the other one also?
Which
I
one?
think number 4.
Number 4?
Yeah, that one has like math or
Alrighty,
something.
let's do it. This is gonna be the one where we're gonna use slides 9.5, that weird table with bond energies. Okay, so if you see me panicking, it's because I'm switching tabs. Okay, so first of all, we have to figure out what kind of bonds we are using to make each of these compounds. So in water, what kind of bond is holding the oxygen and the hydrogen together? Because we have water like this, right? So what kind of bond is between the oxygen and the hydrogen? This one right here. A single bond, right? And then there's gonna be 2 single bonds, right? Because we have these 2 bonds right here. So we're gonna do 2 times, and then according to this table on slides 9.5, the bond between hydrogen and oxygen has an energy of 467 kilojoules, right? So then we're gonna do 2 times 467 kilojoules, right? Plus, and then fluorine, bonded to fluorine, has what kind of bond? This one right here.
Single.
Also a single bond, right? And according to our table, a fluorine-fluorine bond is 158 kilojoules, right? But according to our stoichiometry, we have 2 of these, right? So we're also going to multiply this by 2. And then I'm going to draw this arrow just as a placeholder, or actually, hold on, because I'm going to run out of space. This is going to be, oops. This is going to be reactants, right? So now let's do the products. Okay, now for difluorine monoxide, right? That's what that is. We're going to have oxygen bonded to fluorine, kind of like this, or actually like this, right? So what kind of bond is holding these 2 together?
A single bond.
Also a single bond, right? And then again, according to that table on slides 9.5, we have fluorine to oxygen, right? So that fluorine to oxygen bond is going to have an energy of 190, oops, wrong tab.
So we're going to multiply that by
100.
2?
I'm sorry?
We multiply that by 2?
Yeah, 190 kilojoules. And we're multiplying by 2 because we have 2 single bonds, right? And then last but not least, we have hydrofluoric acid, right? This also has a single bond, right? And that energy on the table is going to be 566 kilojoules, but we have a stoichiometry of 2, so we're also going to multiply this by 2, yes? And then one last thing is, this is the energy needed to, wait, let me double check before I say something dumb. This is the energy needed to break the bonds, okay? So then on the reactant side, we're breaking these bonds so we can use the numbers given on the table. But on the product side, we're making the bonds. So we're gonna, you guys remember back in module 9 where it was like when you flip the equation, you also had to make the number of, or the energy negative? It's the same thing. So on the product side, it's going to be a negative number of what we have. So this is going to be negative 566, and that's going to look ugly. Negative 190, because we're making bonds instead of breaking them. And on the reactant side, since we're taking apart those, that's the energy that we need. So then we keep the numbers as is. Okay. So then now, would anybody be so kind as to give us a simplified number for the reactants and for the products while I look for my calculator? Did anybody get an answer?
Reactants, I got 1250.
Okay. I should probably write that in a different color. And then for the products?
Negative 1512.
Negative 1512 kilojoules. Okay, so then now we're gonna find the difference. You guys remember Hess's law? It's products minus reactants, right? So then we're gonna do, or actually, it should be reactants minus products, because we should get a negative number. So we're just gonna find the difference between these, basically. Okay, so then what's the difference between these two numbers? Anybody? What's 1250?
Negative 262.
Yeah, I have negative 262.
I'm sorry, I
Right?
typed really slow on my calculator.
Don't worry. Negative 262 kilojoules. So then this should be the overall change in energy in this reaction. Or yeah, the enthalpy of reaction. That should be your final answer. I think in the answers he sent, he has a different answer, but then he went over it in lecture and he said this should be the correct answer, something like that. Because I know one of my students asked me about it. Does that make sense to everybody? And again, all of these numbers, I got them from slides 9.5, slide number 2. But if you get a question like this on the exam, you will get whatever information you need.
So it
Okay.
takes negative 262 kilojoules to do what?
To complete this reaction that we have right here, combust water and fluorine gas, basically, is what's happening. So we're
So to
burning
make
water
water
and fluorine
explode in fluorine gas?
Yeah, pretty
Yeah.
much.
That's the amount of energy that's being released, just so you guys know.
Yeah,
When
because
do
it's
you
a
make-
negative number,
How do you
right?
make
So
water
that's
explode in fluorine gas?
because fluorine reactants minus products. Yeah, for the most part, Destiny, to answer your question. Aaron, to answer your question, it's because fluorine is more reactive than water. So water will react in fluorine, if that makes sense.
So if you put water in fluorine, it blows up?
Mm-hmm.
So how come if the products it's negative 100, but it's negative 1,512? How come it's not 1,250 minus negative 1,512?
That I do not know. Do you guys know, Jerry, Alan?
What was the question?
Why didn't we do negative 1512 minus 1250?
Oh, all you're doing is adding. So for this, you're adding up the energies. And so
Okay.
what we ended up doing is instead of subtracting it like normally, like what you would do for enthalpy, since this is bond energy, what you're doing is you're using that bond energy to figure out the dissociation energy, or when those bonds break, and then putting it with the bond energy, which is the products. So it's positive because this amount of energy, this is the amount of energy that they need to absorb in order for them to break. Then the products, it's negative because that's the amount that's released when those bonds are formed.
Okay, got it. Thanks.
Okay. Any other questions on this?
Have you ever
Cool,
done that
gonna-
experiment before?
Sadly, no. I've been in one lab and one lab only, and then the pandemic started. So here's to hoping I get to someday. Alrighty, so which other one do you guys want to go over before we call it quits in 5 minutes? Or do you guys have other questions from study set 16 or anything else in general?
What's number 6?
Number 6. Okay, cool. Let's talk about that. I'm pretty sure this one also has to do with slide 2 and table 5. Slides 9.5. Let me double check real quick. And then, cool. Yeah, okay. So there's two ways, there's two ways to think of this. So we have bromine, bromine, right? Chlorine, chlorine, and fluorine, fluorine. So we know that from what we've talked about, right? Is that the single bond is the strongest bond of a single, double, and triple bond, right? But when you're comparing single bond to single bond, what are two things that you can do? What are two things that you can use to decide if it's a strong or a weak single bond? Also, Alan and Jerry, can you guys get the chat? Anybody? Hint, hint, I showed you slides about it before we started. It's 2 words or 2 concepts. One starts with E, the other one starts with B, and it's 2 words. Anybody still there? Yes, electronegativity is one. What about the other one? Hint, hint, we just used it in the previous problem. Bond energy, exactly. So, when it comes to electronegativity, the more difference in electronegativity you have between the 2 atoms, correct me if I'm wrong, guys, I think it's the stronger the bond is? Or is it the other way around?
I'm sorry, can you repeat what you just said?
Yeah, the difference in electronegativity between 2 elements, does that make the bond stronger or weaker?
It makes it stronger.
Makes it stronger, right? Yeah, so like if you have hydrogen and fluorine, right? That's gonna be a stronger bond than carbon and fluorine because there's more difference in electronegativity between hydrogen and fluorine.
I would use a better example than that one. Like
Okay.
hydrogen and fluorine and hydrogen and carbon maybe.
Okay, yeah. Let's do this. Let's make this hydrogen. Yes? Okay. So, but as you guys can see, these are diatomic molecules. So that means that they are connected to themselves, right? So they don't have a difference in electronegativity because they both have the same amount of electronegativity, right? So we can't use electronegativity in this case because we're bonded to the same thing. Yes? So then the other thing we can use is bond energy. So then if we go to this lovely table that I showed you guys in slide 9.5, a bromine-bromine bond has an energy of 193 kilojoules. A chlorine-chlorine bond has a strength of, 242 kilojoules. And a fluorine-fluorine bond has a bond energy of 158 kilojoules. So remember, this is the energy that you need to break this bond. So based on that and the numbers, which one do you think is the weakest bond? Fluorine, fluorine. Okay, yeah, because we have it, you need the least amount of energy to break it, right? So then the weakest single bond between all of these is going to be the fluorine-fluorine bond because we need the least amount of energy to break it. Does that make sense to everybody? Awesome. Okay, I'll take one more question if you guys are willing. But if not, then we will call it here and we will.
Can we go over 3 real quick?
Yes. Oh, hey, I prepared for this question. I'm ready for y'all. Okay, so if you go on the interwebs and you ask Google if HI is polar, you will more than likely get the answer that yes, HI is polar. However, if you go to Dr. Alexander's answer key, you will see that HI is not polar. And that's going to have to do with, actually, I'm going to share screens for this one. It's going to have to do with this lovely table right here. So what Dr. Alexander is going to do for these is you're going to find the difference in electronegativity. So this is the electronegativity up here. You're going to find the difference in electronegativity between the two atoms. And if the difference is less than 0.5, then it is nonpolar. And if the difference is more than 0.5, then you have a polar molecule. So we have hydrogen here. Let's call this like 2.1, right? And then iodine is 2.5-ish, right? So then 2.5 minus 2.1, that's going to give us 0.4, right? So according to the rules that Dr. Alexander gave us, is this going to be a polar or a non-polar molecule? Yeah, non-polar, right? Because last time I checked, 0.4 is less than 0.5, right? So then that's the way that you're going to, that's the way that you are going to decide between polar and non-polar molecules for Dr. Alexander. Yeah, so then, but, you know, if you go on the logic of the interwebs, when you decide polar versus non-polar, it's just you're deciding which one is more electronegative, if there's a difference in electronegativity. And because iodine is more electronegative than hydrogen, that's why the interwebs says that this is a polar bond. But again, when you're figuring out polarity, make sure that you follow Dr. Alexander's rules so that you get it right on the exam. Does that make sense to everybody? HCN. Okay, yeah, let's do that one. I'm just gonna do a little erasing here, right? Okay, so HCN, let's first draw it. So that's going to be a single bond to hydrogen because hydrogen can only have one bond, right? And then carbon needs to have 4 bonds. So that means we're going to have a triple bond here and lone pair on nitrogen, right? So hydrogen, we said this is going to be 2.1. Carbon is about 2.5. And then nitrogen is 3. So, or actually before we get there, we don't even need to do that. Between hydrogen and carbon, which is the more electronegative element? Carbon, right? So which way should we draw our dipole arrow? Towards carbon, right? So we should draw something like this. Okay, and then between carbon and nitrogen, which is more electronegative? Nitrogen, right? So with that same logic, we're going to draw our dipole arrow towards nitrogen, right? So now, do these arrows cancel each other out or add up to each other? They add up to each other, right? So is this a polar molecule or a non-polar molecule? It's polar, right? Yeah, so that's how you can decide on that. You could also do the math and then the difference between, so the difference between the carbon and the hydrogen bond and the carbon nitrogen bond should be big enough, bigger than 0.5, so then it should still make it polar, because this is going to be 2.1, and then this is 2.5, and then this is 3. So this difference is 0.4, and this difference is 0.5, and then we said they add to each other. So that's going to be a polar molecule, right? Because that's going to be 0.9. Yes? If you want to do it the math way. Oh, he does say it's nonpolar? That's whack. I guess the reason it could be that he said it's nonpolar is maybe he subtracted here instead of adding. So that's going to be, I mean, you can either think of it as negative 0.1 or positive 0.1, but either way, it's less than 0.5. So I think that's why he would go with nonpolar. Yeah, I think that's where that came from.
So do they add up or do they subtract from each other then?
I'm going to go with Dr. Alexander's logic and say that they subtract from each other, which is whack.
So I don't think that's the reason.
Do you have a better reason? Because that's all I'm working with.
I'm pretty sure what he ended up doing was for the carbon and nitrogen that it was ever so slightly less than 0.5 because the nitrogen's not exactly at 3, it's a little less than 3, and so he just rounded it down to make it 0.4 or something.
Okay, so this is probably like 2.9 is what you're saying, or the nitrogen, I should say. Since it's not like right on the line.
I meant for the nitrogen, but basically specifically just for Dr. Alexander, this is non-polar. Because normally carbon and nitrogen would be deemed polar.
Polar, yeah. Ain't that fun? So for the most part though, with Dr. Alexander's exams, whatever he puts on his study questions, that's what's gonna pop up on your exam. So you shouldn't worry too much about like other examples. I mean, like you should, but not too much. Okay. But I think I'm gonna cut it off there unless anybody has any super last minute questions on this problem specifically. Are we good? Gonna take that awkward silence as a yes. So I'm going to stop sharing. Thank you guys for coming. Best of luck on exam 4 and on your final. And the recording should be posted at the latest tomorrow.
So if you have any last minute questions, remember the last day for office hours is tomorrow. There are no office hours on Friday. So if you have anything regarding any module, anything for your final, tomorrow is your last day to do it. So thank you for coming. You're free to go, and good luck everyone on your exams and your finals. It was
Bye,
a good semester, as good as you can make it.
Yeah. Good luck.
What time is the office hours?
On Thursday from
9.
9:30 to 6:30.
9:30 a.m.
Yeah.
6:30 p.m.
Now they're all day. Cool.
Well,
Yeah,
there's
different people, but
Mhm.
yeah, there's somebody there from 9:30 to 6:30.
Yeah,
Cool. Thank you.
you're welcome.
Mm-hmm.
Hey, yo, Alan, can you stop the recording?